Okay, good. I think everything is going to work there. So we have already seen two proofs by mathematical induction from section 5.2. So we're going to continue our games with mathematical induction. There are several really helpful formulas. We already proved the first one. Recall, we proved that the sum of the first n integers is given by this formula, n times n plus 1 over 2. And this is true for all n greater than or equal to 1. All right, so we use mathematical induction, and just to kind of remind you, the concepts of mathematical induction says, hey, if we've got the possibility of proving that the statement is true at some lowest level step, like P of n naught, so we're standing here on this lowest level step, and then if we can prove that if we're standing on step K, that we can step up to the next step, the K plus first step. If we can do those two things, this first thing is called the basis step, where we get onto the staircase. This second part is called the induction step or the inductive step, where we say, if P of K is true, then we can show P of K plus 1 follows. So when we can do these two things, then we can invoke the principle of mathematical induction, the PMI, and we can climb up forever and ever, and the statement will be true forever after. It's a very cool kind of a concept, because what it allows us to do, folks, is it allows us to prove infinitely many statements with a finite argument. And that's actually really cool. We're actually proving an infinite number of statements all in one fell swoop. So let's pick back up now today, and let's do another proof by induction. And this time we're going to prove a formula about not a sum, but a product. All right, so here we go. Our first example for today, example 1. We're going to prove P of n, stated below, is true for all integers n greater than or equal to 2. So in this particular proof, our lowest level step isn't 1, it isn't 0, it's 2. So our n naught, our bottom level integer, is going to be 2 here. And here's the statement. The statement says that the product, it's a big product, from I equals 2 to n of the expression 1 minus 1 over I squared is actually equal to n plus 1 divided by 2n. So this is our statement. It's really a predicate statement, P of n. Okay, so the argument is n here. There's an n here, there's an n here, and there's an n here. And we're going to all remember that we're going to be super careful about how we prove equations. We won't ever start with the equation that we wish to prove. We will work on the left-hand side, and maybe we'll work on the right-hand side. We'll do that separately, show that they're equal in the basis. Or in the case of the inductive step, we'll start with the left-hand side of P of K plus 1, and we'll turn it into the right-hand side of P of K plus 1. So maybe some of this will come back to you as we start our proof by induction. Always tell your reader that it's a proof by induction. So we're going to just state, let P of n be the statement above, or let P of n be given as above. I don't want to rewrite it, and you don't want to waste time rewriting it either. unless you have had in the past some issues transcribing from the screen to your paper, in which case you should go ahead and write this again on your paper on test 3, right? Because I've noticed, especially with these like 2 to the p plus 1, whole thing minus 1, or 2 to the p minus 1, minus 1, people are having all kinds of issues. Y to the x turns into yx, or y over x. I don't know how all that happens, right, for different individuals. So you may want to just, when you see your proof by induction, your statement, you may want to just transcribe it right onto your paper so that you don't have to worry about that issue. All right, we're ready for the basis. The basis step always starts the same way, folks. We're going to just tell our reader what that lowest level step is. So we're going to let n naught equal, and here it's going to be 2, because we're always told where to start the proof. So we're going to start it at 2. And what do we wish? It's always the same wish in the basis step. We wish to show that P evaluated at that lowest level integer, here 2, is true. It's always the same wish. So it's kind of nice because proof by induction is very formulaic. Here we go. We're going to start by looking at the left-hand side, not of P of n, but where the argument n is 2. And let's evaluate that. So the left-hand side of P of 2 is, all right, here we go. We're just going to plug in a 2 where we see the n. So it's the product from I equals 2 to 2 of this term 1 minus 1 over I squared. Now, the lower limit and the upper limit are the same value, and that means we're just talking about the single term that's indexed with the number 2. So we just have only 2 to plug in for I squared. So it's 1 minus 1 over 2 squared. Of course, that's 1 minus a fourth, and that's 3/4. So the left-hand side evaluates to the number 3/4. Any questions so far? Everybody good? All right, so now let's take a look at what happens when we evaluate the right-hand side. The right-hand side, we're going to still plug in a 2 everywhere we see the n. And we'll just tell the reader what we're doing. The right-hand side of P of 2 is, okay, so it's 2 plus 1 over 2 times 2. And lo and behold, that's 3/4. So they both evaluate to 3/4. And we just say that, the left-hand side equals the right-hand side. So P of 2 holds, or is true. You can say it either way. We have just gotten onto the bottom step of this staircase to mathematical heaven. Questions? All right, well, let's start our inductive step. Always skip a line and, make it so that we can tell the difference between working on the basis step and working on the inductive step. Bunch of people got scared off camera. All right, here we go. This always starts the same way too, folks, because what's happening here is we're telling the reader about the integer k. We're getting ready to introduce a new letter. We need to tell the reader what it is. So again, the nice thing is that the induction step always starts the same way for every induction proof. We're going to just say, hey, let k greater than or equal to, and here, whatever that value n naught was, goes here. In other words, we're trying to say, hey, we could be standing on step 2, or we could be standing on one of the higher steps. But the point is, k is an integer. It's just some particular but arbitrary integer. And now here's our inductive hypothesis. We're going to assume P of k is true, i.e., we're going to assume, and here we go, we'll just write it, that the product from I equals 1 to k, you see, we're going to put a k in everywhere we used to see an n. Now here, we're still using an I for the term. The term is 1 minus 1 over I squared. Okay, so that's the actual term value. the term expression, excuse me. We don't put a K here. We need this I, okay, because we need this to represent a product. Did I say some? It's a product of many factors. The first factor is when I equals 1. It'd be 1 minus 1 over 1. In other words, the first factor. Oh, did I put 1 there? What is it? What am I supposed to put here? What's supposed to go there?
Two.
Yes. Did you see what just happened when I put in I equal 1? That first factor would be 1 minus 1 over 1. That means that first factor would have been 0. And then that would zero out the entire product, and the product would always be 0. We don't want that. We want to start with a factor that's not 0. In fact, we don't want any of the factors to be 0. They won't be. Okay, so I equals 2 to k of the quantity 1 minus 1 over I squared, and this is a product. All right, now it's equal to the right-hand side with k everywhere we currently see an n. So it's k plus 1 over 2k. That is our inductive hypothesis. So hence the birth of proof money. This is where it all started. This is our inductive hypothesis. And we're going to have to use this. All right, now let's look at our wish very closely. This is important. Listen, folks, if you can't express the wish, then how in the world are you going to ever prove it, right? We have to be able to say what we wish to show. What do we wish to show? Anybody? This is where we assume we're standing on step K. So we're standing here. And we wish to show that we can step up to the next step. So we wish to show P of k plus 1 follows. This is the inductive step. So we wish to show P of k plus 1 is true. i.e., we wish to show, let's go ahead and write now, P of k plus 1. So now the argument, instead of the argument being k, which it was in P of k, it's k plus 1. So everywhere we currently see a k, we're going to substitute in a k plus 1. Here we go. It's the product from I equals 2 to k plus 1 of this quantity, 1 minus 1 over I squared, is equal to, and now we're going to be real careful. We're going to plug in k plus 1, but then we add a plus 1. So that's our numerator. It's really k plus 2, right? And then downstairs, folks, we're replacing k with the binomial k plus 1. Parentheses are not optional. We must use parentheses here. So, just, if you want to see what this really is, this is k plus 2 over 2 times k plus 1. That's what that really is. Let's close up our thinking notes. To emphasize that this is not what we have in our hand, but that it is a wish. It's so easy to get confused between what you really know and what you wish. It can be helpful to have a visual aid to remind you the difference. We're going to get to use this. This is what we have in our hand, but this is what we're going to try to prove. And we're going to use every trick in the book that we've learned. We're going to separate off the k plus first term of this product. It's a factor. We'll separate it off. We will use the inductive hypothesis to substitute into the product from I equals 1 to k of this expression, 1 minus 1 over I squared. Then we'll evaluate the k plus first factor, do algebra, and then hope for the best. Hope it turns into k plus 1 over k plus 2 over 2 times k plus 1. Here we go. So we're proving a formula. Keep our money where we can see it. And we tell our reader what we're doing, starting with the left-hand side of P of k plus 1. What do we have? Well, we have the product from I equals 2 to k plus 1 of this quantity, 1 minus 1 over I squared. It's kind of an interesting expression, 1 minus 1 over I squared. Because as I gets bigger, right, this amount gets smaller, So we're subtracting an increasingly small amount from 1. So these factors approach 1. As I gets very, very large, we're subtracting a very tiny amount from 1. And we're getting closer and closer and closer to this factor just being 1, if you think about it. All right, so now we're going to just say, okay, this is what we've got. We want to use this. How do we get this from this? Of course, that's where we separate off the k plus first factor. So this is from I equals 2 to k of 1 minus 1 over I squared times, okay, it's a product, folks, not a sum. This is one of the things that's going to happen. A few of you are going to accidentally put a plus here instead of a times, and then things aren't going to work out. The algebra won't work at all if we accidentally use the wrong sign. And this is, operator. The product from I equals k plus 1 to k plus 1 of this same term, 1 minus 1 over I squared. Now, does anybody have any questions about this equality? Does anybody need me to kind of show what we're really doing with that? Does everybody understand this notation? Everybody good? You don't want me to show you more? Okay, that's fine. I'm going to trust you. All right, here we go. Check it out. We have extracted the product from 2 to k of 1 minus 1 over I squared. And that's what we know something about. We know that product is equal to k plus 1 over 2k. So I'm going to indicate that by just putting the square brackets in green around this part of the product that, we've separated the last factor off. And now that can be kind of a visual aid to help us realize, wow, we can use induction and always indicate when you're using your inductive hypothesis by putting a star over the equality where that substitution actually it takes place, excuse me. So we're going to plug in k plus 1 over 2k here, because that's what this is equal to, right? These two are equal according to our inductive hypothesis. This is our inductive step. Now we still have to deal with this broken off factor from I equals k plus 1 to k plus 1 of 1 minus 1 over I squared. And we will do. We'll deal with that right now. I think in WebAssign, they don't even bother to put the sum or product from k plus 1 to k plus 1. I think they skip that step, but I think it's helpful to kind of keep you sorted out. All right, so what do we got? Well, we've got the k plus 1 over 2k. That's what we got from their inductive hypothesis, substitution. And times, and now what is this term going to be, folks? What does this factor look like? Anybody? Just you see what it is? Do you know how to evaluate this? This one. Hello, hello. Anybody?
1 minus 1 over k plus 1 quantity squared.
Perfect. Right, we're just plugging in I equals k plus 1. It's just that single term where I takes on that value, k plus 1, see? So we're just plugging it in right here for the I. And since it's a binomial, we're going to make sure and put parentheses around it. And that's why Hans said quantity squared. All right, now hang on. Let's take stock. See, this is where having your wish is so helpful. Check it out. We want to get this. We started with the left-hand side. See, remember, this is the left-hand side of P of k plus 1. And we're trying to show that this equality holds by actually turning the left-hand side into the right-hand side using legal algebra moves, okay? So this is where we're at. This is what we've got. Let's compare it to where we're trying to go, okay? We want to just get k plus 2 over 2 times the quantity k plus 1. You know, that's pretty simple. It's a single fraction, a single quotient. What do we actually have right now? Yikes. We have a fraction, but it's being multiplied times something that's not even a fraction. It's a binomial that includes a fraction as one of its terms. So we're going to need to try to figure out how to get from this to that. Okay, so the first thing I realize is I'd like to get a common denominator here because it'll be easier to multiply a fraction times a fraction than to multiply a fraction times a binomial, one of whose terms is a fraction. It's like, that's a lot of work. I don't want to do all that, right? So let's just bring our k plus 1 over 2k down. We'll we'll do this multiplication right there in a minute. But right now, I want to get a common denominator. What is the common denominator so that I can pull these together into a single fraction, a single quotient? What's our common denominator, folks?
It will be the k plus 1, I forgot what he called it, square
Quantities.
quantity again.
Yeah, nice, nice. Very nice. So that's Sonia, right? Oh, is that Sophie?
Sophie.
Sophie, thank you. Great. So we're going to use k plus 1 squared as our common denominator. What do we need to multiply the 1 times to put it over the k plus 1 quantity squared? It's over 1 right now. So we need to multiply it by k plus 1 squared. So 1 times k plus 1 squared is just k plus 1 squared. Everybody with me? Okay, good. Now, the 1 here in this fraction is already over the k plus 1 squared. In fact, it's not a 1, it's a negative 1. So we'll just bring it down. Everybody with me? And we're keeping our eye on the prize, keeping our eye on the prize. This is what we're trying to get. This is where we're at. All right, so again, let's work on this numerator of this fraction here, and let's see if it won't simplify a little bit. We've got k plus 1 over 2k times, well, upstairs here, we've got k squared plus 2k plus 1, but then the plus 1 will cancel with the negative 1. So all we have upstairs is k squared plus 2k, and downstairs we've got k plus 1 quantity squared. So what do we got? We've got, just kind of separating things out, we've got k plus 1 up top over 2k times, well, we can factor a k out of k squared plus 2k now, k times k plus 2 up top, and downstairs we have k plus 1 squared. I'm just going to keep my wish where we can see it. Getting closer, we're getting closer to this. All right, check out what cancels. Look, we've got k plus 1 up top. We've got k plus 1 twice as a factor on the bottom. So we can cancel one of these k plus 1s with this k plus 1, leaving just one of these k plus 1s behind. Also, we have a k up top as a factor and a k downstairs as a factor. So we can cancel those. Because you see, these are all just now being multiplied together. This is fraction multiplication. Multiply the tops together, multiply the bottoms together. So what's left after the k plus 1 cancels up top and the k cancels up top with one of the k plus 1s on the bottom and the k on the bottom, we're left with k plus 2 over 2 times the other k plus 1. And that's exactly what we wanted to get. This is, k plus 2 over 2 times k plus 1. So, which is the right-hand side of p of k plus 1. So, yay. Just a little bit of algebra. We squared out this k plus 1, and then this plus 1, factor from foiling, multiplying 1 times 1. We had a plus 1, but it cancels with the minus 1, so we got k squared plus 2k. Factored out the k, canceled a bunch of stuff. And we can now say, so P of K does imply P of K plus 1. So we got P of K plus 1 from having P of K. So we've just proven we can climb the staircase. All right, and now don't forget the last step. You know, I know we say it's the basis step and it's the inductive step, but then we should say it's the PMI step, because there is one more thing we have to do to nail this, and that is to invoke the PMI. We just say by the principle of mathematical induction. You can just say by the PMI. We can now say that this product from I equals 2 to K, n of 1 minus 1 over I squared is equal to n plus 1 over 2n is true for all n greater than or equal to 2. This is always our n naught right there. And you don't even have to say all integers n greater than or equal to 2, because anybody who's reading your proof by mathematical induction knows mathematical induction is about it's about integers. It's always about integers. Questions? Now we're going to have a discussion tonight, a short discussion about what do I do, Dr. Good, if I'm completely stuck in the algebra, okay? So let's take a look at this algebra nightmare, right? What do you need to be able to do to get maximum points, even if your algebra is not as strong as you would like it to be? Okay. Well, you need to be able to start with the left-hand side. You need to demonstrate that you know how to separate off the K plus first term, whether this is a product or a sum. You need to be able to demonstrate that. You need to show the inductive step where you make the substitution, because you have already talked about your inductive hypothesis. You've got to be able to know what your wish is. You've got to be able to write that, because somewhere along the way, even if you get stuck with algebra somewhere in the middle, you have to have been able to make this inductive substitution, and then this K plus first term, you need to be able to evaluate it. So, you know, you need to be able to get down to this far, because this doesn't take any algebra. This just takes substitution and understanding summation and product notation. It also requires you to be able to write P of K. And you have to, of course, know how P of K plus 1 looks. Otherwise, how could you start with the left-hand side if you didn't know what that looked like? So really, to get to here doesn't require algebra as much as substitution and manipulating sums and products. Okay, so you get this far, maybe you get a little further, but the point is all this from here to here, once you get, get this far, from here to here is not going to lose you that many points. You could just say, Dr. G, my Kung Fu is not that strong, right? My algebra isn't great. It isn't up to speed or something, whatever. But the point is, then pick up with this. Pick up here. I mean, just say, hey, I know I want to get this. I know I want to get this. And then so you can just say, this is, I may not be able to get there, but I know this is what I'm shooting for. And then you can go ahead and just invoke the PMI and get the rest of the points. Maximum deduction 4 points on a 20-point problem for not being able to do the algebra. Okay. Questions? All right. So there are a whole nother class of problems that can be attacked using proof by induction that don't have anything to do with formulas, right? If you look at last week's notes from last Tuesday, gosh, it seems like so long ago, a week ago. I wrote 3 different famous formulas. One was 1 + 2 + 3 + ... plus n is the sum formula. And then the second one was 1 squared + 2 squared + 3 squared + ... plus n squared is some formula, you know, some expression. And then the third one was 1 cubed + 2 cubed + 3 cubed + ... plus n cubed. Sum of the first n perfect cubes is equal to some, you know, expression. And we played a lot with that first one, the sum of the first n perfect positive integers. We played with that, right? We showed how useful that is for your special homework that's going to go up right after class. By the way, the next, you know, web assign is already up. So go ahead and get cracking on that stuff. Special homework will be due Friday. The first problem in the special homework is for you to prove that the sum of the first n perfect squares, that's 1 squared + 2 squared + ... plus n squared, is equal to a ratio. Okay. So, but there are a slew of other kinds of statements that we can prove by induction, not just formulas, is what my point is. So let's look now in section 5.3, where we really do start using proof by induction for other kinds of statements, proving statements involving the concept of divides, proving statements using divides. Okay. So these are mathematical induction proofs. Here's our example 2 tonight. Let's prove that 4 divides the quantity 5 to the n minus 1 for all integers n greater than or equal to 0 now. So it's a kind of different kind of game. It looks different than the game we've played so far, doesn't it? Our n naught is this 0. Okay. All right, here we go. I know. Proof by induction. Let n naught equal 0. What do we wish to prove? Anybody? What do we wish? This is our basis step. What do we wish to prove? Oh, wait a minute. I jumped the gun. That's the start of the basis step. That's not the start of the proof. How do I start the proof? That was the basis step. We're going to say, let P of n be the statement. It's really a predicate statement. 4 divides 5 to the n whole thing minus 1. That's the way we start it. Now we're ready for the basis step. If I don't throw my pen away, let n naught equal 0. Now what do we wish to show? It's always the same. Same game over and over again.
Would it be P of 0?
That's exactly what it would be. We are trying to prove P of 0. We wish to show P of 0. But let's go ahead now. It's not an equation with a left-hand side and a right-hand side. Let's talk about what P of 0 is, i.e., we wish to show that this statement that has an n here in the exponent is true when that n value is 0. So we wish to show 4 divides 5 to the 0 minus 1. Okay. But let's dig into our wish just a teeny tiny bit further, because it involves divides, and divides is always noisome, right? So what do we really wish to show? Well, this actually translates to an equation, doesn't it? the concept that 4 divides this expression means this expression, 5 to the 0 minus 1, is a multiple of 4, right? It's equal to 4m, where m is in z. Definition of divides. This is all my wish. This is all thinking notes. This is not part of the proof. This is thinking notes, and it doesn't count. It's like it never happened in terms of the compiler, folks. So we have to, we're going to have to use this to guide the next part of our code, the part that really gets into the proof proper. You see, when we unwind this, it tells us we got to look at 5 raised to the 0 minus 1. That's our job. That's the expression we need to show is a multiple of 4. So we're going to attack 5 to the 0 minus 1. So observe. 5 to the 0 minus 1. What is 5 to the 0 minus 1, folks?
Zero.
It sure is, because 5 to the 0 is 1, and 1 minus 1 is 0. Now, isn't it nice that we have our wish here? See, this is our wish. We can't start with this. This is what we're trying to prove. We are wishing that. How can we show that 0, which is 5 to the 0 minus 1, equals 4 times an integer m? How can we do that? What would be our integer m that's going to work?
0.
Sure does. 0 is equal to 4 times 0. Remember, there was a fact way back when we started playing games with divides, that for any integer n divides 0, except n equals 0. Every integer besides 0 divides into 0, because it's n times 0. That's what 0 is, n times 0. And we just, just say, hey, in 0, I'm talking about this 0 is an element of z. So 4 divides 5 to the 0 minus 1, which makes P of 0 true. So we've got P of 0 done. All right, now we're going to go to our inductive step. Always starts the same. Tell your reader what the heck K is. Let K greater than or equal to something be an integer, a particular but arbitrary integer. We're just going to write integer because we're lazy. What are we going to fill that blank in with, folks? What goes here? Let's look at what we're always told where we're starting, right? And here's where we're starting, right? So this has to be the 0. This has to be the value in naught right there. Because if we didn't start with K at the lowest level value for n, then we wouldn't be able to step off the first step, you see. We have to be able to get off the first step as well as a step that's higher up the ladder. See what I mean? Like, we need to be able to get on the first step. We did that already, but we want to be able to climb the staircase. So if K doesn't start down here at the lowest level step where we're standing at the very beginning, then we wouldn't be able to climb up off that step, you see. So we have to be able to climb off any step that we're at. We're calling that step K. But we want to, at that K value, to start way down at the bottom so we can climb off the first step. All right, here we go. Let K greater than or equal to 0 be an integer. Now what do we say? What is our every time statement inside the induction step? Always got to say it.
We're gonna assume P of K is true.
Yeah, it's nicely done. We're going to assume, email me for a couple of points. You have certainly earned them. Assume P of K is true. That's our inductive hypothesis, always. I.e., let's take a look at what P of K is going to be. Okay, here's P of N. So P of K, we just put a K in where the N is, right? So P of K is the statement that 4 divides 5 to the K minus 1. And we're going to now translate that to an equation because the bottom line is proof money is usually equations, i.e. assume, all right, we'll translate divides here into the equation 5 raised to the K, whole thing minus 1 is equal to 4 times some integer, I'll say J, where J is in Z. This is what it means to say 4 divides 5 to the K minus 1. It means 5 to the K minus 1 is a multiple of 4. So here's our proof money, and here's our information about J. Okay, we're gonna need all that. This is the inductive hypothesis. It's these two pieces of information. All right, let's take a look at our wish. What do we wish to show? P of K plus 1, of course. We wish to show P of K plus 1 is true, i.e. that 4 divides 5 raised to the K plus 1, whole thing minus 1. But you know what? We're going to just take that a step further because it's about divides. Always dogs is here. It's 5 to the K plus 1, whole thing minus 1 is equal to 4 times M, where M is in Z. See, this is our wish now. We can recycle M. We only used it sort of as a placeholder there. We never signed anything, the value M. So when we used M up here, this was inside thinking notes. See, this didn't compile. This isn't compiling either. We can reuse M. So this tells us, hey, we got to look at 5 to the K plus 1, whole thing minus 1. We got to look at this. And this is what we have to use. So let's see how we play that game. There's a critical algebra key here I want to show you. All right, so this is the money we have in the bank. This is what we want to prove. How are we going to get from point A to point B? We are going to start with 5 raised to the K plus 1 minus 1. That's what we want to say something smart about. So observe. 5 raised to the K plus 1, whole thing minus 1 is equal to, we got to work on it now. We want to change it into 4 times M, where M is some integer, right? This is also part of our wish. We cannot start with this. If you start with this, toss it, no good. So this is what you want to do, folks. Look at this. Look at what we have. We have information about 5 to the K minus 1. Well, I see a minus 1. Okay, we've got the minus 1 here. But we got way too many 5s here. How can we extract a 5 to the K, just one single 5 to the K from this? That's the key. Here's the algebra key right here. We can use laws of exponents. Isn't 5 to the K plus 1 the same thing as 5 to the 1 times 5 to the K? Whole thing minus 1. I mean, isn't that good? See, now we see a 5 to the K. Now we got too many of them, though. We got 5 of them here. This is 5 to the K plus 5 to the K plus 5 to the K plus 5 to the K. It's 5 of them. It's like having 5 apples. You know, we only need 1. So here's the other key. The key, you know, turns this lock and this lock. It's a multi-purpose key. It's got to be from IKEA. This 5 can be rewritten as 4 plus 1. Why did I do that? Couple of reasons. One thing, I want a single copy of 5 to the K. And when I distribute 5 to the K across 4 plus 1, I will get a single copy of 5 to the K. The other reason this is kind of nice, that 5 is equal to 4 plus 1, is it gives us a 4. And look, we're trying to show that there's some 4s around. See, there were no 4s in here at all. This at least introduces a 4 into the mix by changing 5 to 4 plus 1. Let's go ahead and distribute this out now. This is 4 times 5 to the k. So we got like 4 apples there. Plus, well, 1 times 5 to the k is just plain old 5 to the k. Minus 1. Ta-da! Check it out. We have now extracted 5 to the k minus 1 from 5 to the k plus 1 minus 1. This is perfectly legal and works. And now we realize, okay, I see 5 to the k minus 1. I can substitute in 4j there, because we know by hypothesis that 5 to the k minus 1 is a multiple of 4j. 4, excuse me. 4 does divide that. So here comes our sweet by induction substitution, where we're going to use our green proof money. And we'll just bring down the 4 times 5 to the k plus, and now we can substitute in 4j for 5 to the k minus 1 by induction. See, we just used that. We're one step away. What should we do now? We're one short, sweet step away from satisfying part 1 of the definition of divides. Look at your wish. What are we trying to do here? We're trying to show.
Factor out the 4.
Go ahead. Go ahead. Go ahead.
Factor out the 4.
Yeah, we need a 4 to factor that out. Is that you, Hans?
Yeah.
Dankeschön. Dankevel. And so we pull out that 4, and lo and behold, this is part 1 of the definition of divides. Right? We got the 5 to the k plus 1 minus 1 is 4 times glop m. That's our multiplier.
I have a question.
Yeah, Sophie, hey.
So, before the induction by induction step, how did you, yeah, right, I think right there, how did you open up the brackets? How did you use 4 plus 1 to multiply? Oh, yeah.
So I
Go ahead.
multiplied 5. It's usually we distribute from the left, like usually we distribute from the left like this,
Yeah,
but you can distribute from the right as well.
okay.
So it's right distribution. It looks funny, doesn't it?
Okay, so it's
5 to the k times 4. That's 4 times 5 to the k plus 5 to the k times 1.
okay, I see.
Yeah, okay, good. I'm so glad you asked. All right, cool. So now we're just going to fulfill the definition of divides all the way here. We're going to show, see, this is our M. We got to argue that that's in Z. We know this game since K and J are in Z. And Z is closed under, what do we got going here? Multiplication and addition. Closed under multiplication. At this point, we're so sick and tired of this, we almost want to skip it, but we're not going to. M equals 5 to the k plus j is an element of Z. Listen, one thing I really noticed on the quiz, and I chopped up your quizzes with lots of writing and your homework. You're welcome. A lot of people forgot to say the cream. Milking the cow, talking about closure, talking about K and J being in Z, and then you just said M equals this and never said it's an integer. That was the whole point of milking the cow, was to get the cream. Okay. So it's in Z. Hey, that's part 2 of the definition of divides done. Thank goodness. We are so sick of that we are just trying to get moving on. So what did we show? 5 to the k plus 1, whole thing minus 1 is equal to 4 times m. where M is in Z, which means, what does that mean? Josue, do you know what this means? What did we just show? This minus sign is very big. It doesn't need to be 5 to the k minus 1, plus 1 minus 1 equals 4 times m, where m is in z. Where did that even come from? Look back at our wish.
Is it P of k plus 1 is true?
Yeah, that 4 divides 5 to the k plus 1 minus 1, which means 4 divides 5 to the k plus 1 minus 1. So P of k plus 1 is true. I was just trying to get us to remember what the heck, we were trying to do. We were trying to show P of k plus 1, which is this statement right there, that 4 divides 5 to the k plus 1 minus 1. So P of k plus 1 is true. Following from P of k, whenever, I'll just go and finish this, whenever P of k is true. That's just another way of saying P of k implies P of k plus 1. And now we invoke the PMI by the PMI. We can say 4 divides 5 to the n minus 1 is true for all n. Where did we start? What was our low level here? Anybody remember what our lowest level was? Our n naught?
0.
Yay. Okay, done deal. So there are 2 proofs involving division and 2 proofs involving formulas. One is a product and one is a sum. So there are 4 proofs in this mini homework that's going up right after class. Okay. Now, we still have a little bit of time, but we're tired, right? We are tired. Let me tell you a story. Let me tell you a story. Story time, boys and girls. Actually, see my bruise? I helped a friend move. I got a big old bruise. I'm afraid I'm gonna get a blood clot, stroke out. I'm just kidding. Do you know that, like, back in the 1600s and 1700s, different mathematicians used different notation, and one mathematician might read another mathematician's notation? It had not been standardized at that point. Like, sequences of symbols could literally be interpreted more than one way in terms of the algebra that they represented. Even back in the Middle Ages, a lot of times what mathematicians would do is they would write their math problems as stories. And this is a true story, true in the sense that a mathematician really couched a mathematical problem as this story. So let me just give you a little background about mathematics in general. If a mathematician is working on a hard problem or kind of a big problem, the first thing that mathematician will do is try to kind of look at the simplest cases and see if they can figure out anything about the simplest cases, like, empty set, or n is 0, or prime is 2 or 3. And then from there, you grow your theories and see what you can prove for bigger and bigger, and what we call more general statements, bigger statements that subsume more of the mathematical world. But we always start simple. So that's the context here, because this is a very contrived story about bunny rabbits. Let me tell you a story. Here is the way it goes. A pair of newborn rabbits, one male and one female. Okay, so it's kind of a perfect world. There's one male, there's one female. Will mate for life. Like I said, it's contrived. Will mate for life and produce one pair of rabbits, one male, one female, every month, starting with the month they turn 2 months old. But there's a little bit more. These baby rabbits that they have, these twin pairs, not identical, obviously, fraternal twins, one male, one female, they mate with each other in the same fashion. Rabbits born together as twins, right, will do the same thing. They start reproducing, they only mate with each other, and they produce one pair of bunsters every month, starting with the month that they are 2 months old. So here's the mathematical question. How many pairs of bunnies? How many? That looks like how many? It's supposed to be an owl. How many pairs of bunnies will there be after n months? All right, everybody understand the story? Okay, so I'm going to draw a picture. You get another Dr. Good cartoon. You get a cartoon. Here we go. All right. Over here, we're going to put the month. And here, we're going to draw the bunnies. All right, so at the month, n equals 0. These are newborn rabbits. It's one male, one female. I'll just draw them kind of small. They're newborn. Okay, that's all we've got. We've got one pair of bunnies. After 1 month, these are bigger. They're teenagers. We'll draw them kind of skinny and tall, but not old enough to reproduce yet because they're only 1 month old. All right, month 2. Haha. These baby rabbits have now had 2 months to become grown-ups. So we'll kind of draw them fat, a little fat. And now they've had their first pair of bunsters. Here's their babies. So we have 2 pairs. Month 3. These adults, it's a month gone by now, they're still at it. They are going to have another pair of babies. And these babies are now teenagers, but they're not old enough yet to have babies of their own. So we have 3 pairs at 3 months. Everybody with me? How many will there be after 4 months? How many pairs of bunsters? Let's see. The grown-ups are still grown. So we have them. Ooh, the teenagers are now grown. The second babies are now teenagers. What am I missing?
Another pair.
Yeah, because, oh yeah, these guys have another pair. And these bunsters that were born 2 months ago in month n equals 2 are now grown-ups and they have a pair. All right, that's month 4. How many pairs? We got 5 pairs. Month 5. How many pairs will we have? Oh, there must be a famine. There's so many bunny rabbits that they're losing food. They're not getting as big as the. Their babies are are preemies. These are now teenagers. But then these have another pair. And these now are grown up, so they have their first pair. Did I get them all? How many pairs?
8.
Yes. Guess who wrote this story? Really, truly wrote this letter. Not even kidding. Didn't use, didn't use my version of English, used kind of an old-timey English. Actually, I think he was Italian. He was Italian. He wasn't writing in English. He was writing in Italian. Do you know his name?
Fibonacci?
It's Fibonacci. Yes, this is the Fibonacci sequence. All right, here we go. And his name is Fibonacci, and it really was a letter that he wrote to a fellow mathematician. This is the Fibonacci sequence. And it's our first recursively defined sequence. Here's the way it goes. Well, let me just show you. It starts like this. F naught is 1, then the next term is 1, the next term is 2, then 3, then 5, then 8. That's how far we got. 1 pair, 2 pair, 3 pair, 5 pair, 8 pair. Do you see the pattern? It's a recursively defined sequence. We have to look backwards to go forwards. Check it out. The first 2 months have to be given to us. These are our initial terms. 1 and 1 are the first 2 terms in the sequence. And then this is the way it goes. You add those together to get the next term. 1 plus 1 is 2. Now we have a sequence 1, 1, 2. You add the last 2 terms together to get the next term. 1 plus 2 is 3. That's how we get the 3. Now the sequence is 1, 1, 2, 3. To get the next term, you add the last 2 terms together. 2 plus 3 is 5. 3 plus 5 is 8. What would the next term be?
13.
Yes, indeed. And what would be the one after that?
21.
That's right. Here's our definition. F sub 0 is 1. F sub 1 is 1. And of course, the sequence is called capital F because of Fibonacci. And then F sub k is equal to F sub k minus 1 plus F sub k minus 2 for all k greater than or equal to 2. This is the Fibonacci sequence. It is a recursively defined sequence because we have to look backwards to go forwards. This part is called the initial terms for obvious reasons. You can't just bootstrap from nowhere. You gotta have some boots. And then this part that tells you how we build subsequent terms from prior terms is called the recurrence relation. This is the beginnings of chapter 5.6. We're going to pick up with chapter 5.6 on Thursday. We aren't going to be doing that much. I just want to just gently dip into 5.6 because the real meat on the bones of our lecture Thursday is chapter 7 about functions. And I even have dug up an old test. An old, oh no, look at, oh no. An old test, if somebody just moved in, it's kind of crazy, isn't it? That's got test-like questions from chapter 7. So I'll be posting that on Thursday after lecture. And then on Tuesday, we'll do chapter 8. And then we'll be having test 3 on Thursday. What I'd like to do is just say test 3 is going to start at 7 next, a week from, it's what, the 18th or the 19th of, the 18th of July. We'll have a Q&A from 6 to 7 on Thursday, and then at 7 we'll have the last test. But there's still plenty of stuff to do. You know how much work we do in a week and a half, so we still got good stuff. Special homework's going to be posted in here in a few minutes, and your web assign's already up, and you've got proof by induction web assigns that have been up. So enjoy. Questions? Answers? Hey, thanks for playing. Anybody who participated and all who participated, appreciate your participation. I'm going to call it a day. I'm going to stop recording here unless anybody has a question.